So, in this half bridge converter we see that the switch S1 or D1 or the switch S2 and D2 may be conducting. So, how do they conduct? It is shown in this slide. Here we have given the gate signal to S1 and the gate signal to S2 here. So, if S1 gate signal has been given, then the upper switch turns on, the voltage between point A and O will be like this here. Suppose the current waveform is alternating in nature. So, sometimes the current is positive and sometimes the current is negative. Let us take the interval T1 where the current is positive while the voltage between points A and O is 0, which means the lower switch is on. During this time we have now two possibilities. Either S2 will be on or D2 will be on, and we see that because the current is positive direction, that means the current is flowing from left to right, only D2 is conducting, because D2 has this path and the path of the current is like this. So, the path of the current is shown here, this is the path of the current, and D2 is conducting. So, the circuit is getting completed like this, D2 I load and like this here. So, we see that in spite of giving pulse to S2 during this time, the IGBT is not conducting, it is the diode D2 which is conducting, and the voltage between point A and O is 0, because if it is an ideal diode, the voltage drop across the diode is 0. So, basically point A and O are at the same potential. Now, let us take the second interval T2 here. During the time interval T2, we see that we have given gate pulse to S1 while the current is still positive. If this is the case, then we see that okay, we have given the gate signal to S1. So, which means either S1 or D1 will be on, and since the current direction is positive, therefore, the IGBT here must conduct, because this is the path of the current. So, it is flowing through the IGBT through this here through the current source and then through the voltage source, and there is the path complete. So, during this time interval T2, we see that the voltage between point A and O, because switch S1 is conducting, the voltage between point A and O will be equal to Vd. Next, let us see the case during time interval T3. So, we are looking now into this time interval T3. During this time, we see that the gate signal has been given to switch S1 while the current is negative. So, since gate signal has been given to S1, so the either S1 or D1 will be conducting here. In this case, since the current direction is negative, that means the current is now flowing from right to left here, the current must now flow through diode D1 here, and when diode D1 is conducting, assuming an ideal diode, the potential at this point and at this point becomes same, and hence the voltage at point A with respect to point O will be equal to V d. So, we get a positive voltage. So, VAO here is a positive voltage, the diode D1 is conducting and the current is negative here. Let us take the last case where the gate signal has been given to the switch S2 while the current is flowing negative. In this case, we find that switch S2 is conducting here. So, we have analyzed the 4 switches of the half bridge converter and when they will be conducting at different time instants. In summary, we can say that the voltage, that is VAO, produced by the half bridge converter is unidirectional in nature, while the current can be bidirectional in nature. Before I go to full bridge converter, I must stop here for a minute and explain something which which needs some attention. So, if you see here, we have so far talked about a circuit like this, where we have said that this is point O and this is point A and this is point O. This is the circuit which we have talked about. Often we represent this circuit as something like this. Two switches, ideal switches, bidirectional switches. Now, in many literatures and also in books, you will find an alternate representation. What is the alternate representation? The alternate representation, in the alternate representation, we have a circuit something like this, VAO like this. What is the difference? First of all, understand that this circuit here, in this circuit the point O is actually an imaginary point, it is a fictitious point. In a real circuit, if you analyze, say for example, you analyze a half bridge, how will you get the DC bus of the half bridge? You will do it from a rectifier. For example, the rectifier circuit, say if you take a 3-phase rectifier, here comes the DC bus. The DC bus is, so this is a 3-phase rectifier and here is the DC bus. The DC bus is or is made up of capacitors, and there is no midpoint of these capacitors unless someone makes a special connection to get a midpoint of the capacitors. Normally it is just a capacitor, there is no midpoint. However, in many books and literatures also, you will find that the O point has been taken here. Now, this means there is a reason for it. Remember, this O point is an imaginary point, it does not exist in a real physical system. Now, if you analyze the two circuits, for example, suppose we analyze these two circuits, then we see that here the VAO voltage, the VAO voltage is always fluctuating between 0 and VD, where VD is this voltage here. The VAO voltage always oscillates or fluctuates between 0 and VD. On the other hand, the VAO voltage here always fluctuates between VD by 2 or minus VD by 2. So, we see that in this case, the when they say, for example, in you have S1 and S2 here and S1 and S2 here. If S1 is on in this circuit here, if S1 is on, then VAO is VD by 2, if S2 is on, VAO is minus VD by 2. On the other hand, here if in VAO it is 0 or VD. So, we see that if we use this circuit, then there is always a DC in VAO voltage produced, because it is always oscillating between 0 and VD, whereas in this circuit we always oscillate between plus VD by 2 and minus VD by 2. These two circuits are equivalent, only the difference is that in this circuit there is always a DC offset in VAO waveform. So, the presence of this DC offset or the DC offset, if we can remove it by using this circuit, the analysis becomes much more simpler. And so, many people prefer to use this circuit here with O point at the middle. Many people prefer this circuit to be analyzed because the DC offset in VAO voltage does not exist in this circuit, but this circuit analysis is more close to the real system. So, therefore, we can use either of them, but in the present analysis we will use this circuit here all the time, because this is more real, this is closer to the real system. So, this VAO is between 0 and VD, this is what we will assume. However, remember that this analysis with plus VD by 2 and minus VD by 2 is also equally valid. Now, so far we have analyzed the half bridge circuit. Now, let us add one more leg to this converter. Okay. which is called in fact the full bridge converter. So, here you see that so this is one half bridge and we have added one more half bridge to the circuit. Note that these two half bridges are completely independent of each other. In fact, they do not know their existence, they are just operating independently. So, the left hand half bridge does not know about the right hand half bridge. So, here why are we then adding this second half bridge? The second half bridge is added mainly because we want to get bidirectional voltage across the load. Remember, in the half bridge, with a single half bridge we got unidirectional voltage and bidirectional current. Now, with a full bridge it is possible, we will see this later, it is possible to have bidirectional voltage across the load. But more importantly, there is another advantage. The advantage is that we get double the voltage from the same DC link using the full bridge as compared to the half bridge. So, how first let us understand how the full bridge is operating. So, in the full bridge, of course, as I told you, there are two half bridges which are operating independently of each other. So, if you want to get, so there is now this leg, there is point A here and there is point B here. So, if we want to get the VD voltage here, then you can turn on S1 and S4. If you turn on S1 and S4, then if you turn on S1, then A point is shorted to the positive terminal. If you turn on S4, B point is shorted to the negative terminal, and so the voltage VAB is equal to the DC bus voltage. As you can see here, if this is turned on, so which means that this point is shorted to this point and this point is shorted to this point. If I turn on S1 and S4, the diagonal switches, if they are turned on, so I can see that the voltage VAB is nothing but VD. Similarly, if I turn on the other two diagonal switches, and these other two diagonal switches are say S3 and S2 here, then I can get minus VD across the load. On the other hand, if I turn on both the upper switches or both the lower switches together, then I get a 0 voltage across AB, because if I suppose I turn on the lower two switches, then A point is shorted here, B point is shorted here, and I get a 0 voltage here. Basically, the load is freewheeling during that time. It also happens when you turn on both the upper switches, it is like this here. Now, similar to half bridge, where we analyzed the operation of all the four, I mean 2 diodes and 2 transistors, here also we can analyze the operation of all the 8 switches here. I will not go into that details, but I will only analyze 1 or 2 of them. For example, so there is a VAO voltage which is VD, and then there is a VBO voltage which is shown here, and it depends on how we have applied the gate signals. In this case, the gate signal S1 and S4 is applied, so VAO voltage becomes VD here, and gate signal to, if you apply here, it becomes VBO like this. So, during this time, what is the VAB voltage? VAB voltage is nothing but VAO minus VBO. VAB voltage is VAO minus VBO. I should write it here as VAB is equal to VAO minus VBO. So, I can see that if I subtract VAO minus VBO in these two curves, I see that VAB voltage fluctuates between plus VD and minus VD here. Now, the current can be again, depending on the power factor, the current can be sometimes positive and sometimes negative with respect to the VAB voltage. So, let us take the time duration T1 where the VAB voltage is minus VD and the current is positive. And so, I can find out which are the switches conducting. So, first I will see that okay, I have applied the gate signal to S2 and S3. So, these two diagonal switches must be conducting at this point. Now, out of them, which one is conducting, whether the diode is conducting or the IGBT is conducting, that can be understood from the direction of the current. So, here the current direction is positive. So, which means the current is flowing like this. So, it must flow like what is shown by the dotted line here, diode, the current, and through this diode D3 and then comes back. So, this must be the path of the current here. What is the voltage? So, VAB voltage. So, because the diode D2 is conducting, so O point is shorted to A and D3 is conducting. So, B point is shorted to the positive terminal and therefore, the voltage of minus VD is getting applied across VAB here. In a similar way, you can also do the analysis for other durations. For example, if you take the T4 duration, you can make a similar analysis and can find out that the switches S3 and S2 are conducting, just like how we have done with a half bridge. So, in this fashion, it is possible for us to know all the 8 switches, the 4 transistors and 4 diodes, how they are conducting in this full bridge converter. Okay. But remember that one advantage of using a full bridge is that in a half bridge, remember that the load voltage was fluctuating between 0 and VD, whereas in this case in a full bridge converter the load voltage is fluctuating between minus VD to plus VD, which means that in a full bridge converter 2 half bridges are working together and we can make them work in such a way that we get double the voltage out from a full bridge converter as compared to the half bridge converter. Okay. So, this is the other advantage of a full bridge converter as compared to a half bridge converter, although we are using more number of switches, but we are getting double the voltage across the load. Okay. Now, before the next step in our analysis, we will see what is called as a pulse width modulation. Why do we use pulse width modulation? Because we want to control the voltage magnitude across the load. If you see here in, for example, the full bridge, the voltage magnitude across the load is always fluctuating between minus VD and plus VD. and we cannot control the output voltage magnitude. So, by introducing notches in this voltage waveform, which we will do using pulse width modulation, we will be able to control the output voltage magnitude. So, let us see how we can do it. So, what we will do is we will turn on and off these switches S1 and S2 repeatedly by following a specific pattern. So, let us see how we can develop this pattern. So, in this pulse width modulation technique, the output voltage is controlled by a series of pulses of voltage. So, if the pulse width is more is the average voltage across the load, or more is the output voltage of the converter. So, in this technique there is one high frequency triangular wave. So, this is the triangular wave, which is part of the triangular wave is shown here. Basically the triangular wave exists like this. Okay. So, this is the high frequency triangular wave, and we also have this as the modulating wave or the reference wave. So, there is a high frequency carrier wave or the triangular wave, and it is compared with a low frequency modulating wave or a reference wave. The low frequency reference wave can also be a DC. For example, in this diagram you can see that the modulating waveform here is not changing over the time interval which we are considering here. So, the red one is the modulating waveform here, its value is m. The triangular wave is spanning between 0 and 1, as you can see here, this is the 1 and there is the 0 and 1. The triangular wave or the high frequency carrier wave is spanning between 0 and 1, and the modulating wave at this instant of time is somewhere in between, and its amplitude is m. Okay. Now, in order to control the output voltage of this half bridge, we follow a logic. What is the logic? The logic is, if the modulating wave is more than the triangular wave, then I turn on S1, otherwise I turn on S2. So, let us apply this logic and see how the output voltage of the converter can be changed. So, here is the triangular wave and here is the modulating wave. So, if the modulating wave is greater than the triangular wave, I will turn on S1. So, which means that during this portion of time, the modulating wave is more than the triangular wave during this portion of time, and hence I will turn on S1. In this circuit I will turn on S1. As I turn on S1, the VAO voltage will be equal to VD, that is the DC bus voltage. The rest of the time, for example here or here, the modulating waveform is less than the triangular waveform, and so I will turn on S2, that is the lower switch, and therefore I will get a 0 voltage here and here. So, you can now see that by changing the height of the modulating waveform in comparison with the triangular waveform height, I can change the width of this pulse which is coming across VAO. So, if the modulating waveform is lower, for example, if the modulating waveform is somewhere here, then I will get a very narrow pulse. So, if the modulating waveform is somewhere here, then I will get a very narrow voltage waveform here or a narrow pulse, and VAO, you can understand the average VAO will be low in magnitude. On the other hand, if the modulating waveform is high with respect to the triangular waveform, I will get a big pulse like this. I will get a big pulse. So, therefore, by changing the position of the modulating waveform in comparison with the triangular waveform, I can change the average output voltage VAO. Okay. The instantaneous output voltage VAO is always fluctuating between 0 and Vd. However, the average output voltage of VAO can be changed by changing the position of the modulating waveform with in comparison with the triangular waveform. So, what is the average voltage of VAO during the switching cycle Ts? So, when we say about average voltage, we must specify a time period, that is the time period in which we are going to do the averaging. So, this time period, in this case we are assuming the time period of the triangular or the carrier wave. So, these terms are used often frequently, triangular wave or carrier wave, modulating wave or reference wave. These terms are interchangeably used. So, in this case, in the Ts period time period, we have the VAO waveform here shown like this, and we can get what is the average VAO during this time period Ts. What is the average value? So, for that we will do some very basic geometrical analysis. So, we see that in this triangle AEC, we see that AB is to BD is equal to AE is to EC, right. So, what is the height of AB? Since this is 0, this is 1 and this height is m. So, the height of AB is 1 minus m. What is the height or what is the length of BD? Now, in order to find out what is the length of BD, we define a term T on. T on is the time for which the upper switch or S1 is on and we are getting a voltage waveform here. So, this is the time period Ts and this is time period Ts by 2 and then there is a T on time period here. So, the length BD will be equal to Ts by 2 minus T on, which is shown here, Ts by 2 minus T on, that is the length of BD. What is the height AE? Height of AE is 1 and what is EC? EC is nothing but Ts by 2. So, this is the Ts by 2 here. So, if I simplify this expression, I get m equal to T on by Ts by 2, which is nothing but the duty ratio. So, which means the time period for which the switch is turned on over the half the switching period. So, the average voltage of VAO during the switching cycle Ts, the average voltage during this time Ts VAO average is equal to, what will be the average? The duration of time for which the Vd is on. So, the duration of time for which Vd is on is Vd into T on by Ts by 2 plus the rest of the time it is 0. So, therefore, 0 into Ts by 2 minus T on divided by Ts by 2. So, the VAO average over this time period will be equal to m times Vd by substituting m is equal to T on by Ts by 2 here. I will repeat this once more. The average voltage of VAO during the switching cycle Ts is Vd into T on, is the time for which Vd voltage has been applied across VAO. So, Vd into T on divided by Ts by 2 is the period here, and for the rest of the time 0 voltage has been applied. So, 0 into Ts by 2 minus T on is the duration for which the 0 voltage has been applied over a time period of Ts by 2. Now, this means VAO average is equal to Vd into T on by Ts by 2, and this T on divided by Ts by 2 which we have derived earlier is equal to m. So, therefore, VAO average is m times Vd, which is also understood from this figure, because if m is equal to 0 we do not get any average voltage, if m equal to 1 we get the full average voltage. So, if m is 0 the modulating waveform is down here, if m equal to 1 the modulating waveform is up here. Okay. So, VAO average is the average voltage in a switching cycle Ts, which we have just now derived. Now, if we start to vary the value of m slowly from cycle to cycle, okay. In this particular cycle which we see here, the value of m is constant over the switching cycle, but suppose in the next switching cycle we just change the value of the modulating waveform slightly. So, for example, which I have shown it here in this diagram, the value of the modulating waveform in one switching, the first switching cycle is here, in the second switching cycle it has been slightly increased, the third switching cycle here it has been further increased slightly. So, if m is varying slightly from cycle to cycle, then what do we expect? We expect that the average voltage will also vary from cycle to cycle, right. So, the average voltage will also change in each cycle. So, if now we change the value of m sinusoidally over a period of time, then the average output voltage will also vary sinusoidally, okay. And this is how we generate a sinusoidal output from a converter. See, for example, I show you this diagram here. In this diagram we see that the reference waveform is changing sinusoidally, but it is changing sinusoidally very slowly as compared to the time period of the triangular waveform. The triangular waveform frequency is much higher than the frequency of the sine wave. So, in a small portion of the triangular waveform period, the sine wave, it seems, is not changing at all. So, it is more or less fixed. So, this is what I had shown it here in this diagram. In the triangular period, the modulating waveform is almost like fixed, it is not changing, because the frequency of the triangular wave is very high compared to the modulating wave, and that is what I had shown. In fact, I had zoomed a small window of this waveform here, and I had shown in the previous slide. This slide here was a small window of this waveform which I had, which was the full waveform. So, if m varies sinusoidally and slowly over time, then the VAO average will vary sinusoidally with time. Okay. Now, you may argue, what do you mean by VAO average varying? So, sometimes in order to differentiate, people have used the term instantaneous average voltage in this case. Instantaneous average voltage means over a time period Ts, the average voltage is m times Vd here. So, this is the instantaneous average voltage, whereas once m starts to vary here, then we get a sinusoidal output from the converter, and it is only valid, this assumption is only valid if the triangular frequency is very high as compared to the modulating waveform or the reference waveform. For example, the modulating waveform can be a 50 hertz or a 60 hertz signal, whereas the triangular frequency can be 5 kilohertz or 10 kilohertz or even higher. So, during a small portion of the triangular period, we can safely assume that the modulating waveform sinusoidal is fairly constant, right? Yes. Now, one important thing, if m does not vary sinusoidally, then so now we have come to this point when we say that the output voltage of the converter can be varied, and that can be varied by using the modulating waveform as a sinusoidal waveform. If I use a non-sinusoidal waveform, can it be done? In fact, yes, it can be done. For example, suppose this is the triangular waveform, and we are generating a sinusoidal waveform from the triangular wave. But from our understanding, the waveform need not to be sinusoidal. For example, if suppose we have a waveform like this and I want to generate something like this, okay, from the converter, then it is also possible. So, the modulating waveform need not to be a sinusoidal waveform. In fact, it can be a higher order harmonic waveform also. The only condition that we have to preserve is that the frequency of the highest component in this non-sinusoidal waveform which we are generating, the frequency of this, the highest frequency component in this waveform must be very less compared to the frequency of the triangular waveform, or in other words, the frequency of the triangular waveform should be much higher than the highest frequency of the waveform that we want to generate, typically 15 times higher, 10 to 15 times higher. So, this kind of a non-sinusoidal waveform is used, for example, in active filters, where the converter is asked to produce a non-sinusoidal waveform containing different harmonics, and in that case we must have a triangular waveform which is even higher than the highest frequency harmonics that the converter is producing. So, coming back to this concept of sinusoidal PWM, we see that by changing the modulating waveform slowly and sinusoidally over time, we can generate a sinusoidal output voltage from the converter, and this is nothing but called sinusoidal PWM.